now that we've learned something about how neural networks can be used to model input-output mappings, functions, I'd like to talk a little bit about the theory behind that and the fact that neural networks can, in theory, be used to model any function. So I'm going to describe to you and prove to you at least a simpler version of something called the universal approximation theorem. So the question is, can we approximate any function using a neural network? So just to set up, given a function f of x, can we find the weights w sub j, alpha sub j? So j here is indexing these hidden neurons. Can we find weights for this layer and decoding weights, which I'll call them over here, and biases, n of them, such that our function f of x can be approximated by this sum here. So this is really just the input-output of a neural network. You see this here's the input current to the hidden nodes, and then this is the sigmoid function, the activation function. And then once we have this here's all the h's then, h sub j, and then we decode by multiplying all those hidden nodes by their corresponding weights, and then we get our output y, and which I called y, but we want y to approximate f of x. We want that to be to arbitrary precision. So in other words, no matter what f of x is, we can find the w's, the thetas, and the alphas that make our network reproduce f as close as we want. So here's a statement of the universal approximation theorem taken from this paper here. So I'll read it first, then we'll talk about it. Let sigma be any continuous sigmoidal function. Then finite sums of the form g of x equals this, that's basically the sort of thing I just wrote down, are dense in the set of continuous functions on the interval I. In other words, given any f, a continuous function over the interval I, and any epsilon that's bigger than 0, there is a sum g of x of the above form such that g of x is within epsilon of our target f of x for all x's in that interval. So just to fill in some of the gaps here, or some of the pieces, I said it, but maybe I'll just be more explicit here. This here is the continuous functions. On I sub n. So I sub n then is some interval. You can just think of I sub n as being maybe the n-dimensional hypercube, 0 to 1 hypercube. So this says that there exists these alphas, these w's, and these thetas that model any function f as close as you want. So it talks about sigmoidal functions. So sigmoidal function, sigma of x, is any function that goes to 1 as x goes to infinity and goes to 0 as x goes to negative infinity. So logistic function, for example, does that. You can imagine a shifted and scaled hyperbolic tan function. So there are lots of different functions that do that. The threshold function also does that, like the Heaviside step function does that. So we'll use that in a minute. So the theorem states that there exists a big N, and this is basically the number of hidden nodes, and there exists weights wj, biases theta j, and weights alpha j for j equals 1 to big N, such that g of x is within epsilon of epsilon of f of x. So here's the proof. Suppose we let the weight w go to infinity. So we're going to sort of simplify things and think of these sigmoid functions as just threshold functions or Heaviside step functions. So to do that, we're going to let the weights go to infinity. All the weights will go to infinity. So a logistic function or any of these sigmoidal functions, if you let the w go to infinity, I can zoom this out a little bit here, go to infinity, don't like that infinity, then we get 0 for x less than or equal to 0, and then we get 1 for x greater than 0. So you can, if you remember what a sigmoid or logistic function looks like, it passes through 0.5 at 0. So sort of a standard logistic function looks like that. But as you crank up that w, you get more steep versions. And at the limit, you get this here. A step function. It's a Heaviside step function. So another way to make our lives a little bit easier, let's look at a shifted version of it. So as w sub j goes to infinity again, we're cranking up that gain. We got this other shift b sub j. So if you work that out, this is 0 for x less than or equal to b sub j, and it's 1 for x greater than b sub j. So it's just a shifted version. So here's b sub j, and so our function looks like this. So it's a shifted Heaviside step function. And so Heaviside step function is just the limit of, as w goes to infinity, and so we'll define the shifted Heaviside step function as the limit as w goes to infinity of sigma w x minus b. So this Heaviside step function has two inputs. The gain, has two inputs, x and the shift b. Now we're going to use two Heaviside step functions to create a little, what you might call a boxcar function. A function that's 0 way out far to the left, 0 way far out to the right, but in this little particular box, it's equal to 1. So this thing I'm calling a piece, p, is a function of x, and it has sort of a location where it starts, then it's got a width, delta. I'm going to define it as Heaviside of b minus Heaviside of, let me redraw that, Heaviside of x shifted by b shifted over just by delta. So let me do a different color here. So the Heaviside function, nope, don't want that. The original one, the one in red, is like this. Oh, I'm erasing things now. Red. The blue thing looks like this. So if I subtract those two, I get, how should I draw it? I'll draw it in green. Well, I can do it down below. If I subtract the two, I get this. I believe it's open there. Oops. No, I think it would be, it doesn't really matter in that, but I think it would be closed there. I have to think about that. Pretty sure they'd be open. Okay, whatever. I'm not too concerned about those limit cases. But you can see that we have a little piece. That's 0 everywhere. So really, we can use this piece as kind of like a little tile and model our function f of x by putting a whole bunch of these tiles down. That's what we're going to do. Okay, since f of x is continuous, that means the limit, I'm just reading this thing out here now, this is the definition of continuity. It's continuous. So f of x goes, as x goes to a, the limit as x goes to a of f of x equals f of a. And so there's another theorem called intermediate value theorem or mean value theorem, a number of different, not mean value theorem, intermediate value theorem, theorems that sort of combine the guarantee this next sort of thing that I'll write down. There exists an interval, and I'll call it aj to aj plus delta x, such that f of x minus f of aj is less than epsilon for all x in the interval aj to aj plus delta x. So now in a picture, we're centering things on, or we're starting things at aj. So here we are, and we've got this function value here. I'm saying that there is an interval, which I'll call delta x, such that everything, all the f values in that interval are within epsilon of this level here. So if I go up an epsilon, I get this level here. And if I go down an epsilon, I get this level here. And you can see that in this box, which maybe I'll draw as blue, I don't sort of wander more than epsilon away from f of a. So that's just kind of a pictorial view of that thing. So for all x's in this little interval delta x from a sub j to a sub j plus delta x, I don't get further than epsilon from f of a sub j. Okay. So now I'm going to use this fact to construct these pieces that guarantee I never wander further from epsilon away from my target function f of x. So I'm going to choose b sub j. Here I'm going to construct these now. B sub j is going to be just at a sub j at the beginning of my little interval. Delta j is just going to be my delta x. And alpha sub j is going to be my function value at a sub j. So therefore f of x minus f of a sub j less than epsilon for a sub x between a sub j and a sub j plus delta sub j is the same as writing f of x minus alpha j times my piece. Well, I'm going to construct, so this second line I'm writing is not the same as the first line. Now I'm putting in the piece of my approximation of f. The piece evaluated x starts at b sub j with delta sub j, and it's less than epsilon in that same interval. It's basically the same. I'm about to draw the same picture I drew up here. I'm starting here. Now my piece is basically going to hold that value for delta x, or what I'm calling delta j. So then this is a sub j plus delta j. And since I already chose that delta sub j to guarantee that I don't wander more than epsilon away, then I'm fine. Oops, I'm erasing again. Epsilon up, epsilon down. The way I drew it is kind of close. This thing here is alpha sub j times p of x, starting at bj with width delta j. The max error in the interval bj to bj plus delta j is less than epsilon. So this shows you how to make one piece for that interval. You just repeat that process at alpha j plus delta j. You just say, okay, let's make another piece. And of course, the width of the next piece, or the width of each piece, depends on what epsilon constraint you're given. If you're given a really restrictive epsilon, then you have to choose a smaller a smaller delta. You're going to need more pieces, and we'll come back to that in a minute. Okay, so once I have all these pieces, I construct my g of x as the sum, j equals 1 to n, of alpha j p of x b j plus, oops, no, like that. So now, since these p's are constructed from sigmoid functions, then my entire g is constructed of sigmoid functions. I guess I kind of skipped over that. Maybe I should say that here. P is constructed of sigmoid functions. Joke break. Okay, here's a joke. A Freudian slip is when you mean one thing, but you say your mother. Okay. So if I had this function, f of x, and I wanted to, and I had some particular constraint epsilon, maybe a couple millimeters, whatever, I can place down those pieces here and adjust the width so that I never go more than epsilon away from my function. So starting at the beginning here, it's a fairly shallow slope, so I can take a pretty big step. Now I've got my next value here, but maybe the slope's starting to pick up now, so maybe I have to take smaller steps here. So I've constructed that f of x out of a bunch of those pieces, and ultimately then is constructed out of a whole bunch of sigmoid functions. Okay, let me show you a quick demonstration. Here's some Python code, and I can make this available to you. So I've got a function. I've created this piecewise constant function, or this what I'm going to demonstrate demonstrates the modeling a function with a piecewise constant pieces. Okay, that's what piecewise constant means. So I'm going to create some complicated function. There's some function. Now I'm going to split the domain into intervals. Basically 0 to 1 is my domain I'm interested in. And I'm going to take steps of 0.1. And so there are the function values of all those different places. Now I've got this function. I won't go into the details, but it basically, you give it, let's see, you give it a list of breakpoints, kind of like the x values, and you give it the corresponding y values, and it'll create a piecewise function for you. So for example, I've got these breakpoints, x equals negative 0.5, 1.5, and 6, and the corresponding y values that it's supposed to hold. So for example, between negative 0.5 and 1.5, it's supposed to hold a value of 1. So when I give it, I don't actually show, let's see, 1.6. So 1.6 is in this range, so it should hold a value of 3. So sure enough, when I evaluate that function at 1.6, it returns a value of 3. Everything to the left of negative 0.5 returns a 0. That's evaluated at negative 4. And everything to the right returns a 0. So this last thing shows that you can actually call this piecewise constant function on multiple x values, negative 0.5 and 50. Oh, sorry, it holds the last value for eternity, I guess. So when I evaluate it at 50, I get the last value of negative 2. Okay, anyway. So let's fit that function f I showed you before with a whole bunch of those pieces. I'm going to use 10 pieces. So there you go. This shows I didn't choose my width according to the slope of my f. I just chose a constant width. The max error here is 1.0. Whoops, I can't highlight that. Is 1.035. So that happens here, I guess. If I take more pieces, smaller steps, if you will, you can see my error goes down quite a bit, and you can sort of see visually why that's the case. The price you pay, though, is you have more pieces, right? There's more computation required to do this. And if we keep going along that, we're going to rerun this experiment many times for lots of different piece sizes, from size, well, from 1 piece to, I guess, about 200 pieces, or just short of 200 pieces. You can see the maximum absolute error goes down. I don't know if this is actually exponentially, but it goes down asymptotically towards 0. That totally makes sense. Okay, so now you might be wondering, why would we ever need a neural network with more than one hidden layer? So one hidden layer, this theorem shows that with a single hidden layer, you can get arbitrarily close to modeling any function you want. So the question is, why would we ever make a neural network with more than one hidden layer? The problem is that the number of hidden nodes, number of neurons in that hidden layer, will depend on that epsilon, that your epsilon constraint. So if you want, or depend on the function as well. So if you have a complicated function with a really tight epsilon, you might need thousands and thousands and thousands of hidden neurons. In fact, there's no way to know ahead of time necessarily how many hidden nodes you might need. So, okay, so it's an existence proof that it shows that there exists a neural network with a one hidden layer that can get arbitrarily close to any function or any continuous function that you want.